Good evening, Sunderland.
Good evening.
A pleasure to be here, if only virtually, for this talk on JWST+3. It's been 3 years since the James Webb Space Telescope was launched on Christmas Day 2021, and this is a little bit of an update. So there it is, being packed away. On the left-hand side, you can see it being built, and then a little bit of origami in the middle there to fold it up, to put it on the top of a rocket and launch it on Christmas Day 2021. And because it was launched on Christmas Day, I've made these updates, JWST+1, +2, +3. I've made these relatively short Christmas talks, hence the holly and ivy in the corners. So let's just remind ourselves where it went. After launch, it took about a month or so to arrive at L2, where it was placed in a halo orbit. So that means that the James Webb, along with a few other spacecraft, are orbiting Lagrange point 2, sitting there 1 million miles above midnight. On this side of the sun, of course, is the midnight side of Earth. Noon is on this side facing the sun. Midnight is facing away from the sun. And L2 is Lagrange point 2, which is effectively hovering 1 million miles above midnight of Earth. And the James Webb Space Telescope is doing a halo orbit, an orbit perpendicular to the plane of the ecliptic, around that particular point. It's there so that its sun shield, when facing the Earth, shields it from the heat of the Earth, the heat of the moon, and of course the heat of the sun. So by placing it at L2, the telescope can look out away from Earth, and being an infrared telescope, it wants to keep itself as cold as possible, and the sun shield blocks all the light from the sun, the Earth, and the moon. So let's have a think of what it's supposed to be doing. One of the purposes of the James Webb Space Telescope, by working in the infrared, is to look back as far back in time as possible. Why does working in the infrared take you back in time? Well, in principle, it doesn't. Looking at distant objects takes you back in time, because the finite speed of light means that if you're looking at a distant object, you're looking at it as it was, perhaps many billions of years ago. And because of the expansion of the universe, effectively stretching light, the so-called redshift, as the universe expands, light from distant objects gets stretched by the expansion of space. And so any light that originally was perhaps in the visible part of the spectrum gets stretched into the infrared part of the spectrum. So the most distant galaxies will probably be brighter in the infrared than they are in the visible. And hence it's expected that James Webb, working in the infrared and with a larger mirror than the Hubble Space Telescope, should be able to see more distant galaxies and hence see further back in time. This timeline across the top here takes us from the Big Bang on the left to the present day, 13.8 billion years after the Big Bang. So now on the right hand side corresponds to no stretching of light, so a redshift of, we denote redshift by a value of Z, meaning how much has it stretched compared to its original value, the wavelength of the light. A redshift of 1 corresponds to looking back to galaxies as they were approximately 5 billion years after the Big Bang. And we can go back to a redshift of 4 corresponding to a little bit less than 2 billion years after the Big Bang. A redshift of 4 is about the maximum you can hope to catch a distant galaxy without using a telescope. In other words, it is possible to take an image of a distant galaxy using a camera, but not using a telescope, back to about Z equals 4. But if we want to go beyond that, back to the earliest times of the universe, we need a telescope, preferably a large telescope. In particular, we want to get back to this very early period in the first billion years of the universe, which is when we think the first stars and the first galaxies were born. And that is one of James Webb's primary tasks, is to access that tiny window of time back in the early universe. If we expand that up a little bit so we can see it a little more clearly, there's the first 500 million years or so expanded out, 100, 200, 300 million years since the Big Bang. And you can see there above them the redshifts that we would need to see. We'd need to see a redshift of 10 corresponding to wavelengths of 1 micron being stretched to 10 microns. And if we want to go back further, we would need to go to a redshift of 14 or a redshift of 30, as indicated by the diagram there. So far, the Hubble Space Telescope has been able to take us back to galaxies with a redshift of about 10. So that corresponds to galaxies from about 500 million years after the Big Bang. And already we find stars have been around for a long time, and apparently galaxies have been around for a long time. So James Webb hopefully can push that back even further, perhaps as far as 200 or maybe even 150 million years after the Big Bang. That is the hope. So let's remind ourselves of what the James Webb was doing. First light was taken in 2022, and there was a lot of media hype behind the first images and the first spectra coming out of the James Webb. But let's regard that now as history. Of course, there were some wonderful images that came out at that time, back in 2022. Remember the wonderful pillars of creation that were imaged more than once by the Hubble Space Telescope. But being a very dusty environment, it's very difficult to see inside those pillars of creation. As well as the James Webb being able to look back in time by looking at very distant galaxies that are brighter in the infrared, using the infrared light, the James Webb is also able to see star forming and planet forming regions. Because these are very dusty environments, and because infrared light penetrates these areas more readily, in other words, visible light is readily scattered, making it very difficult to see what's going on inside these structures, with infrared light, we can peer inside. And so back in Halloween of 2022, they released this rather ghostly image of the pillars of creation. Here, it's the same image as the last one, but here it's been processed in such a way just to give it a slightly more spooky sort of appearance. But again, this is ancient history. Let's have a think about some of the images that have come out of the James Webb Space Telescope in the last year or 18 months or so, in the third year of its operation. So let's have a look at something from March of 2023, about 18 months ago. This is a Wolf-Rayet star, Wolf-Rayet 124. This is a star that is very unstable, and the nebula that you can see around the star is the result of this star shrugging off its outer layers. It's been doing this for probably thousands or perhaps tens of thousands of years. And this sort of knotty appearance to the nebula indicates that it goes through episodic episodes, if you like, of shrugging off outer material into the interstellar medium. It is thought that perhaps Wolf-Rayet stars are an intermediate stage before a star wants to go supernova. This particular star has been estimated to have a mass of about 30 stellar masses, and it's already lost something like 10 solar masses into its nebula. So this is a very massive star, and it's a prime candidate for being a supernova before too long. And it's thought that perhaps a lot of supernovas actually go through a Wolf-Rayet phase prior to the supernova itself. In April 2023, we were treated to this image of the rings of Uranus. It's a reminder that the rings are very bright when you look in infrared, because the rings are lots of small icy particles. They reflect sunlight very effectively in the infrared, and so the rings appear much brighter than they would in a visible image. And this particular image reminds us that in this case, you see this very bright speck on the left-hand side of the planet. That's thought to be a storm system. When Voyager passed Uranus back in 1986, it didn't see any surface features of any note. Perhaps that was just unlucky. Perhaps Uranus was simply relatively quiet as Voyager sped past. Remember, when you have missions like Voyager visiting Jupiter, Saturn, Uranus, Neptune, it only spends a matter of hours actually passing the planet, and so you only get a short snapshot. telescope images like this, they may not have the resolution of a spacecraft that is right next door to the planet, but a spacecraft like the James Webb is able to revisit Uranus effectively as often as you like, and hence you can follow storm systems and other changes that we weren't lucky enough to see when Voyager went past the planet. Back in May 2023, we saw this image from Fomalhaut from the James Webb Space Telescope, indicating that there's a planetary system in the making here. There's obviously structure within this cloud. There's at least 3 rings. It's possible that we're seeing something akin to an asteroid belt and perhaps a Kuiper belt. It's not quite the same scale as our own solar system. The star itself is blacked out in that central black disk there, and we're seeing the dusty environment indicating that we're seeing a planetary system in formation. We can compare that with a planetary system that we'll see towards the end of the talk. Pandora's cluster is a huge cluster of galaxies. It was previously imaged by Hubble, and here James Webb has gone back to look at it once more. But because of its greater reach, because of the larger mirror and the fact that a lot of galaxies are brighter in the infrared, especially the more distant ones, what we're seeing here is many, many more galaxies than the Hubble Space Telescope was able to collect in the same effective image. This is actually a mosaic, a little bit larger than the original Hubble image. It's been estimated that the total number of sources in this particular mosaic is something like 50,000. It is a huge number that can be analysed to give us an idea of how galaxies are arranged in space. Pandora's cluster is actually lensing some more distant galaxies. Pandora's cluster is some 3 billion light years away, but its light from more distant galaxies is being lensed by the gravitational mass of the cluster itself. For its first anniversary, the James Webb Space Telescope released this image of the Rho-Ophiuchi cloud complex, or at least part of it. At the bottom, we see a star that seems to be excavating a cave in that large yellow nebula, and we see lots of these red jets, that are coming out of star systems, including this one large one here, and other jets in the right. This is coming from stars that are being born. The Rho-Ophiuchi area is one of the closest star formation regions to the Earth. It's about 400 light years or so away, and so this is an area where there's a considerable amount of stars being born. When I first saw this image, I was a little confused because Rho-Ophiuchi is a common target for amateur astronomers, and I couldn't quite figure out where this image was taken. So I thought, if I go back to one of the images I took some years ago with a 135mm telephoto lens, if I blow up the region in the top right, I'm struggling to find which region the James Webb was actually imaging in that previous image that we've just shown. But eventually I tracked it down to the center of that inset. So in the bottom right, that small smudge we can see in the middle there, that is the image that James Webb has just taken. And the difference in scale, it's a sobering reminder that the difference between taking a 135mm lens and the James Webb Space Telescope, which has an effective focal length more like 130 meters, it's a reminder that the focal length difference between an amateur photo and the James Webb is something like 1,000-fold. So not surprising, the actual field of view of the James Webb Space Telescope is tiny compared to the field of view you can expect if you put a telephoto lens on a camera and take pictures of the night sky. Not surprising, but it's nice to see that factor of 1,000 actually appearing. Okay, August 2023, supernova 1987, the supernova that went off in the Large Magellanic Cloud. Here what we're seeing is, given that the supernova went off as seen from Earth quite a few years ago now, what we're seeing is a lot of material that's been thrown off from the supernova in this sort of ring structure here. A lot of this material was probably thrown off long before the supernova actually went off itself. Like we saw with the Wolf-Rayet star, when a very massive star becomes unstable, approaching the end of its life, it will shrug off some of its outer layers into the interstellar medium. And what we're seeing here, this ring of pearl effect that you can see here, this pearl necklace, what we're seeing is the shock wave of the supernova itself catching up with all of the material that's been shrugging off perhaps for thousands of years prior to the supernova. So the shock wave is now slamming into that material, the interstellar material that's now been enriched with all the material thrown off from the star, and the shock waves are producing these bright points of light. And indeed, if we were to follow this year on year, as James Webb will be doing into the future, we will see that ring of pearls structure changing as the shock wave moves through the interstellar medium. September 2023, a very nice image of a star in the process of being born. Again, a very dusty environment, visible light, very difficult to see what's going on. And even here, it's difficult to see what the star is actually doing because there's so much dust in this central region blocking the star itself, we cannot really see what the star is doing. But we can see jets being expelled from the star as the cloud of hydrogen is contracting to form the star. These jets are formed, and these jets are producing shock waves as the jets fly into interstellar space. We tend to think of the interstellar medium as being, well, there can't be much there because surely there's just space in between the stars. But no, the interstellar medium is actually full, in inverted commas, of material, and we can see that from these jets producing shock waves as the jets from the star in the process of formation are slamming into the atoms and molecules of the interstellar medium. This particular system, it's thought that maybe the sun started in a similar way, except that closer inspection of these jets gives a rather braided impression rather than just a rather smooth set of jets. So it's thought that this braiding might be the result of this being the birth of a binary system, perhaps the first time we've actually witnessed the birth of a binary star. This will be monitored in the future to see if we can see changes in those jets as a function of time. In October 2023, the second brightest gamma ray burst of all time was recorded, and James Webb had a look to see what was going on. Perhaps not the most spectacular image. There it is, that tiny red dot here, a so-called kilonova. This was thought to be the merging of two neutron stars. It seems a bit odd, but it looks like that pair of neutron stars was actually kicked out of the galaxy on the right-hand side here. So in other words, this pair of neutron stars was kicked out possibly 1 million years ago, possibly when they were born. And these stars have been rotating around each other, flying off away from their home galaxy. And then those two stars eventually have spiraled into each other and merged to give us this gamma ray burst. So it isn't simply the fact that it was a very bright gamma ray burst that was interesting. What I found interesting about this particular result was when they looked at the spectrum of this particular object, they found traces of a particular element, tellurium. This is element number 52. It's more than twice as massive as iron. So this is a very interesting result. It tells us that merging neutron stars can make heavy elements beyond iron. Remember, all the elements up to iron can be made in the fusion factories that we call stars, fusing hydrogen to helium to carbon, nitrogen, oxygen, silicon, etc., all the way up to iron. But heavier elements must come from something else. And it was previously assumed that heavy elements come from supernova, but now it's fairly clear that merging neutron stars can generate heavy elements as well. I think the jury is still out in terms of how many of the heavy elements, everything beyond iron, how many of those elements come from supernova and how many come from merging neutron stars. We don't necessarily know exactly what that balance is, but clearly merging neutron stars are a source of elements heavier than iron. A very interesting result in its own right. Another object revisited by the James Webb, the Hubble Space Telescope, of course, has already imaged the Crab Nebula some 20 or so years ago, and here the James Webb is seeing it in infrared light. A very milky appearance in the background. This is the result of very energetic electrons emitting light, so-called synchrotron radiation, because these electrons are moving in the magnetic field generated by the central pulsar. You can see some of these wispy lines that sort of trace out some of the magnetic field lines of that central pulsar. If we have a look at a particular feature within the James Webb Space Telescope image, and we compare that with an image taken 20 years ago with the Hubble, let me just point out this object. If we watch this as I jump to Hubble and back to James Webb, back to Hubble, back and forth, you notice that the James Webb image is slightly larger than the Hubble image. That's simply because there's 20 years between them. This supernova went off, as seen from Earth, approximately 1,000 years ago, back in 1054 AD. And so 20 years as a fraction of those 1,000 years is about 2%. So not surprisingly, the image from James Webb is something like 2% larger than the Hubble Space Telescope image, because we're seeing 20 years more of the expansion of the supernova remnant from the supernova that went off 1,000 years ago. November of 2023. Again, a rather striking result here with James Webb in collaboration with another telescope, Chandra, which is looking in the X-rays. So in the background image, the white and somewhat smaller galaxies that are a little shade of red, this is imagery from the James Webb Space Telescope. And the purple glow that you can see covering a lot of the image, this is the X-ray emission as seen by the X-ray satellite Chandra. And what's interesting here is that James Webb and Chandra have managed to pin down the same object in the center of this square. So there's a very bright object seen by Chandra, indicating that anything producing that many X-rays is thought to be a black hole. But when we look with the James Webb in the infrared, we see simply a very small, relatively faint object. So it looks like we've got a faint galaxy with presumably a supermassive black hole at its core, producing a very bright set of X-rays. What's important here is that because we can see the host galaxy of this supermassive black hole, James Webb Space Telescope is able to take a spectrum of this galaxy and determine its redshift. Its redshift turns out to be Z equals 10, and that tells us that we're looking at a very distant galaxy. We're looking at a galaxy going back to the earliest times, only a few 100 million years after the Big Bang. So this is thought to be the first supermassive black hole that has been definitively identified after the Big Bang. So trying to work out how supermassive black holes form, and in this particular case, how they form so early, is a key part of understanding the very early universe. Trying to figure out when the first stars were born, when the first galaxies were born, and in this case, when the first supermassive black holes existed. Because at this point, it looks like even at a Z of 10, black holes, supermassive black holes, bright enough to produce bright X-ray image, seem to have existed even this early in the universe. So the theorists have got a lot of thinking to do to try and figure out how they existed quite so early in the universe. Coming up to 2024, this is simply a montage of lots of spiral galaxies that are relatively close to us. So instead of seeing the galaxies simply as tiny dots in the distance, these galaxies are close enough to us that we can actually see the structure in exquisite detail from the James Webb. And this is simply a montage of some of the galaxies, and you can see they come in all shapes and sizes. This is just a set of spiral galaxies to give us an idea of how these spirals form. By taking images like this of hundreds of different galaxies, we can get better models for galaxy evolution. Jumping a few months now to June of 2024, a rather nice image indicating that we've got, again, a very young set of stars being born here. So this whole region is a hydrogen cloud which is collapsing to form the birth of lots of new young stars, possibly only 1 million years old or so. Apart from being a rather lovely image, this was quite important because it's proved something that we've suspected for quite some time. If we have a look at the various jets that are formed, these red hydrogen-rich jets that are being produced from these stars, they seem to be lined up in particular directions. We can see 1 or 2 or 3 of them where the cursor is, and over here another couple, 2 or 3, and others dotted around the image. In other words, there are lots of stars producing jets, and it looks like most of those jets are lined up. They seem to be always lined up from top left to bottom right in this image. So that would indicate the stars are all spinning in the same direction. That's what we would suspect. If you've got a large cloud of hydrogen and it's collapsing, you would expect that the stars formed wouldn't necessarily form with random spin directions. There might be some randomizing effect, but if they're all born from the same cloud, you might expect a lot of these stars to be spinning in the same direction. And the jets which are coming out in the spin direction of the star do seem to indicate that a lot of stars being born in this image are indeed spinning in the same direction. So again, this helps with our models of how stars are born from collapsing clouds of gas. Still in the same month, June of 2024, JADES is the JWST Advanced Deep Extragalactic Survey. What they've been doing is surveying as many galaxies as possible. A lot of these galaxies are very small and very difficult to see structure, but by taking combinations of the galaxy images and galaxy spectra, it's been determined that there are lots of supernova in a field such as this. And this is important not simply to try and understand how many supernova can we expect to see, but if you take a lot of supernova, if you take a lot of redshifts and you see a lot of supernova at a given redshift, the question is, are they all the same brightness? The redshift would indicate their distance, and the brightness, well, if they're all the same brightness, that tells you that yes, all the supernova are essentially the same. They are good standard candles. Supernova have the same intrinsic brightness. However, if you were to take a lot of data and supernova at the same redshift showed a variation in brightness, that would indicate that maybe supernova are not particularly good standard candles. And given that we are using supernova to give us a calibration of distance, how we convert redshift into distance is using these supernova. It is absolutely fundamental that we understand whether or not these supernova are good standard candles. If James Webb starts to show us that there are some variations in supernova brightness, even at the same distance, that tells us we've got to be very wary about how we calibrate our distance measurements. So that will be very important work going forward. In June of 2024, we saw this astronomy picture of the day, and this is the most distant galaxy seen up to this point. It doesn't look particularly spectacular. We've blown up a tiny dot of light from the center of this, and the inset, it simply looks like a little blob. Now, actually, this is 2 objects. It might not look like it, but this is 2 objects that happen to line up coincidentally. The red object is the more distant of the 2, and that's the interesting one, and the redshift of this object turned out to be a redshift of 14. That puts it at only 300 million years after the Big Bang, takes it back to something like 13.5 billion years ago compared to the 13.8 billion year age of the universe. Now, what was interesting about this object, apart from its enormous distance, was it turns out that this object is something like a little bit more than 1,000 light years across. That doesn't sound like much. Remember, galaxies were smaller back then. Galaxies grow by collisions and mergers, and so we wouldn't expect to see large galaxies. So seeing a small galaxy, well, that's fair enough. But it tells us that the light that we're seeing here, which is spread over 1,000 or 2,000 light years or so, is not coming from the black hole at the center. It's coming from the stars. If it was the black hole, it wouldn't appear to be 1,000 light years across or so. So that tells us that at least for this star and possibly a few others, The main light source from those galaxies is the stars, not the black hole at its centers. Whereas for other galaxies, it appears to be the other way around. For other galaxies, we appear to be imaging the black hole at the center, the accretion disk around that black hole, but not necessarily seeing the somewhat fainter stars. So if we think about where that fits on our timeline that we showed earlier, there's the timeline expanded at the bottom there, redshifts 10, 14, 30. So the James Webb has managed to go back in time so far to this point, Z equals 14, 300 million years after the Big Bang. So it might be that continuing to look at different galaxy fields, it might be that we can see even more distant galaxies. Perhaps we can push that redshift 14 to redshift 20, redshift 25, maybe even as far as redshift 30, who knows. That will take a little bit of time to identify these galaxies, but perhaps we can start asking the question, did galaxies exist 200 million years after the Big Bang or 150 million years after the Big Bang? Was 300 the earliest we're likely to see, or were there even earlier examples? The second anniversary image released by the James Webb was this one called The Penguin and the Egg. Perhaps you can see why. Some people think the galaxy on the right looks more like a hummingbird than it does a penguin, but okay. These galaxies probably passed close to each other, maybe 50 or so million years ago, and they are in the process of coalescing. But as they moved close to each other, the galaxy on the left almost certainly disrupted what was a spiral galaxy on the right, and the spiral arms have been completely distorted into the shape we see there. Not only distorting the spiral arms, but also producing some new star formation along the way. In August 2024, it was thought that they need to have some sort of an update on some of these distant galaxies. That was simply because when galaxies were first imaged in 2022, there were a lot of sensational headlines in social media and other places saying James Webb has seen galaxies that are far too old, the universe is broken, we have to throw away the physics textbooks and rewrite everything. Well, not so. It simply means that some of the earlier redshifts that were calculated have shown that these galaxies, some of these galaxies, are not as distant as was first thought. Some of these galaxies were thought to be very distant simply because they were very red. However, later analysis of redshifts have shown they're a little bit closer, so perhaps not as old as we first thought. And some are distinctly less massive. Some of them indeed are quite bright, and it was the brightness of some of these galaxies that was a little bit confusing when they were first seen. But now it would appear that many of the galaxies, or at least some of the galaxies that have been imaged at relatively large distances, some of these galaxies are less massive than was first thought and first headlined a couple of years ago. And so it would appear for a number of those galaxies that we are seeing light from the supermassive black hole, perhaps not light from all of the stars in the galaxies. So there's still this tension between the two. Some galaxies have a very bright supermassive black hole, and that's what's being imaged. Whereas, as we saw in previous slides, some distant galaxies, we are seeing the stars, not seeing the supermassive black hole at the core. And we really need to understand what the relationship is between the two in terms of why do some galaxies have very bright supermassive black holes and others less so, because that will determine what sort of distance we can see these galaxies. So more work still to be done there. This one I quite liked. This is a galaxy called ARP 107, released in September 2024. It's a nice detailed image taken by the James Webb Space Telescope, but I quite like this one because it was imaged by the previous infrared telescope, Spitzer, which was decommissioned a few years ago. Spitzer was a lot smaller telescope, so it had lower resolution, and with a smaller mirror, it couldn't image the same distant galaxies. So if we compare this James Webb Space Telescope image with the same image taken by Spitzer, you can see much lower resolution, and we don't see those faint galaxies in the background. If I jump back to the James Webb again, you can see so much more detail, plus all of the distant galaxies that are caught in this same image. So again, this is a colliding galaxy pair, the one on the left disrupting what appears to have been a spiral galaxy on the right, and again producing some new star formation along the way. I just thought that was interesting because of the comparison with Spitzer. This was described in the science release from September 2024 of the James Webb. This was described as an odd galaxy, which is a bit of an odd way of describing any galaxy. There it is in the box, just a tiny dot, and even when you blow it up, you don't see much more. But by comparing the image and its spectrum, it was determined that this particular galaxy, which is something like a billion years after the Big Bang, so it wasn't one of the very earliest galaxies, but we're looking at it as it was something like a billion years after the Big Bang. This is a situation in which the gas of the galaxy appears to be outshining the stars. You can tell that by looking at the spectrum, because the light from gas has a different spectrum to the light from stars. So this particular galaxy seems to be producing a lot of light from the gas and not so much light from the stars. Now, it's thought that this could well be a signature of what was happening if a galaxy is made of population 3 stars. Population 3 stars are the very first stars to form, stars that were born from just the primordial hydrogen and helium, and so haven't had time yet to generate the heavier elements, and they weren't born from the heavier elements made from other stars. So, if you like, first generation stars. But this galaxy doesn't appear to have population 3 stars in it, but it does seem to have a lot of gas that is outshining its stars. So if this galaxy isn't made of primordial population 3 stars, because again, they don't have the right spectrum, then why does a galaxy like this have so much gas that's producing so much light? Another mystery which needs to be sorted out if we can understand the origins and the very early history of these galaxies. We're getting very close to up to date now. Here's an image taken from a couple of months ago. This is October 2024. I like this one simply because it's another combination. It's a collaboration between Hubble and Webb. The whitish areas have been imaged by Hubble, and the rather redder areas have been colored in from a Webb image. Hubble and Webb have very similar resolutions. The Hubble mirror is smaller, but it tends to work at shorter wavelengths. The Webb mirror is much larger, but it tends to work at larger wavelengths. And given that the spatial resolution, the smallest thing you can hope to resolve in an image, is based on the relationship, the ratio between the size of the mirror and the size of the wavelength, then it turns out that Hubble Space Telescope and the James Webb Space Telescope have very similar resolutions. And here we're seeing the marriage of those two images, and we can see that Webb gives us more information than Hubble purely does, because we can see that there are some regions which are emitting in infrared which are not readily visible in the visible part of the image. These two galaxies are thought to be in collision, but perhaps one is sliding behind the other. They're not colliding head on. One is passing past the other, and so they are disrupting each other and again giving rise to new star formation, but not actually colliding and not yet merging with each other. The last image that I could find from the science releases of the James Webb was in this month, November 2024, and this is imaging the disk around this star Vega. It's been imaged by Hubble. Hubble had some difficulty trying to block out the very bright star Vega. Remember, Vega is a magnitude 0 star, so it's very bright. So trying to see anything just next to the star is rather difficult. There's a few, presumably, stars in the background there, but very little structure other than the artifacts that we can see as a result of trying to block the star. When Webb imaged the same object, here again, Vega has been blocked out by that central black circle. And what we see now is the dust, the debris around Vega. It is thought that most of this stuff would be, well, perhaps the size of a grain of sand. something like that, from microns up to perhaps millimeters. And we are seeing no sign of any large planets in development. There is some sense of a ring there. That simply means that different sized particles have been blown to different distances by the stellar wind of Vega, because different sized particles are affected differently by the solar wind and pushed to different parts of the solar system. But this particular solar system seems to be something comparable to the Kuiper belt, but there's no sign of any large planets. There's no sign of something like Jupiter or Saturn or Neptune or Uranus being made in this system. Perhaps it's because of the temperature of Vega. Perhaps it's because Vega is a relatively young star. It's only something like 1/10 of the age of our sun. But it does still produce some interesting data, because it gives us a comparison between those stars that we know have got planetary systems. Remember Fomalhaut from earlier, where it looks like there is a planetary system in development, and we know that we've seen fully developed planetary systems. Kepler has found lots of planets around another stars. Here we're seeing a star which does not seem to be developing a planetary system. So that in itself is useful information, gives us more information about planetary formation around stars. So that brings us pretty much up to date. This was JWST+3 because I wanted to give you an update of how things have been going in its third year. It is now effectively 3 years old, in the sense that it was launched on Christmas Day 2021. It's now 3 years old as far as that's concerned. And of course, it has many, many years ahead of it. Because of the precision with which it was placed at L2, it is hoped that it's got enough fuel to position itself and keep it in the L2 halo orbit for another 10, 15, maybe 20 years of wonderful discoveries to come. So I won't necessarily be giving updates every year for the next 30 years or so, but obviously there will be very interesting results to come from James Webb in the years and hopefully the decades to come. So thank you very much for listening. And as a reminder that the James Webb was launched on Christmas Day, may I wish you all a very Merry Christmas. And I bet you didn't know that Santa's sleigh was a prototype for the James Webb Space Telescope. Thank you all for listening.